Okay, so right, part 4 of our Key Stage 4 look at waves. Yeah, we're getting towards halfway there now. We started off back in lesson 1 looking at the differences between transverse and longitudinal waves. Then we had a look at amplitude, wavelength, frequency, speed. If you don't know what those 4 things are, you need to go back to lesson 2 and have a look at that. Last lesson we were looking at sound and ultrasound, the differences between our human hearing, animals, different types of animals, what they hear, and also this ultrasound realm of really high frequency sound waves. So today what we're going to do is we're going to have a look at seismic waves. So we're going to have a look at different waves, how they travel along the Earth's surface. So tectonic plates. Now anyone that's done geography, you should recognise this diagram here. This is the tectonic plates. So obviously our Earth is covered on our what's called a mantle, so the top covering of the layers of rocks, and these are split up into tectonic plates. Now seismic waves are most commonly, and I do stress most commonly, a side effect of earthquakes. Now what this is the movement of tectonic plates. So what we've got down here is our Atlantic ridge, or we've obviously got our ring of fire, which is over here towards India. So as these tectonic plates move, now whether they be moving across each other, alongside each other, i.e. a slip shift side tectonic plate, or whether they be converging or moving away from each other. These movements, normally the slip tectonic plates, as these move, this creates a lot of energy. It creates waves that move apart from these tectonic plates. And these different waves, there's 2 types of waves. They're called P waves and they're called S waves. Now, no prizes for guessing. P stands for primary and S stands for secondary waves. So what we're going to do, we're going to have a look at how these 2 different types of waves differ from each other, and generally what they do after they've emerged from what's called the epicenter of earthquakes. So our P waves start off with our primary waves. Now these are like sound waves. They have the same similar properties to sound waves in terms of the fact that they're longitudinal waves. So I don't know if you can see here, we've got points of compression, or if we've got along here, we've got our hammer hitting the bottom of our block here, and this is causing a compression which is moving up through the solid material that we have here. So as I said, they're longitudinal waves. They act very much in the same way as sound waves do. They travel, they must have a medium to travel through, but they're very good at travelling through those mediums. So through air they'll travel at the speed of sound roughly. Through water they'll travel a little bit faster because it's a bit denser. And through solid, they've been recorded through granite as travelling up to 5,000 meters per second. So that's pretty fast. So as I said, they will travel through solid and they will travel through liquid. They will travel through air, but because of the concept that we're talking about in terms of it being a tectonic movement, or it being waves created from tectonic movement, generally you would obviously find them moving in the material of the Earth, along the mantle or on the outside of the Earth. Now, when we're talking about S waves, we're talking about secondary waves. These are transverse waves. So instead of there being a point of compression, these waves have a vertical movement as well, or a vertical vibration, sorry, not a vertical movement, because obviously it's still a wave, there's no material actually moving from one place to another. All it's doing is carrying that vibration in a transverse way, so our vibration is at 90 degrees to our movement. Now these will only travel through the solid material. The reason for this is something called shear stress. Now, not shear as in, oh God, this is so stressful, but shear as in a sheer face and a straight face. Shear stress will not go through a liquid because liquid's too malleable, so therefore if you just cut through it, it will just go, if you went to sort of karate chop it, you'd karate chop straight through it, whereas if you went to karate chop I don't know, some semi-set sort of moderately solidified custard, it'd be a lot more solid than the liquid would be. So you could go like that and you would watch it wobble, but because the liquid is actually still compressed underneath the mantle, it won't travel through that liquid. And also transverse waves travel a lot slower than primary waves. The secondary waves travel a lot slower than the primary waves do, roughly about 60% of the speed of the primary waves. Generally speaking, S waves are said to be more destructive than P waves. Because P waves are just a compression and expansion, the Earth would only, or the surface would only literally move from left to right, or it would just compress and then move back out again. Because these F waves have a vertical movement as well, or the wave itself moves with a vertical vibration, that would actually cause more, or generally speaking, causes more damage at the surface. So as we were saying before, this is a sort of cross-section of the Earth, really, and which just shows how different how the P waves and the S waves would travel. So if we say here we've got our epicenter, so this is the point of where our vibrations have started, so we'll call it our earthquake here. And as we said, you know, P waves will travel through anything, but S waves will not travel through. S waves will not travel through a liquid. So so here we've got a shadow zone, and this shadow zone is where the S waves, where they can't travel through the liquid, are obviously they're getting stopped by this barrier here. Now, because of this actual shadow here, although it's down as a P wave shadow zone, it's technically also an S wave shadow zone as well, because the S waves can't travel past this part of the liquid centre of the Earth. But because we know that they can't travel through there, we don't really call it an S shadow wave, because we never expect them to get there anyway. But what actually happens here, the interesting point, going back to our laws of refraction with waves, is that as it goes from this solid, the P waves go from this solid into our liquid centre, its course is refracted through the liquid, because obviously it's slowing down, so therefore the angle of it is changed. So as it enters here, and then comes back into the solid, its path is changed again. So it just means that this section here and this section here, away from our epicentre, you wouldn't reach, or you wouldn't be able to record any of these P wave vibrations. Whereas down the bottom, where they have travelled through this liquid, you would still be able to record P waves, but you still wouldn't be receiving any S waves, because they would have been completely blocked off by this liquid. Okay? So it's just a little table quickly, just to go over the quick points, or the quick main differences between primary and secondary waves. So primary are longitudinal, they're very fast, and they can travel through solids and liquids. Secondary waves are transverse waves, they're much slower, about 60% of the speed, and they can only travel through solids. Okay, so that was our look at seismic waves, the two different types of seismic waves. Looking at how waves are produced, and we looked at the two types and the differences between those two. So yeah, that's the end of today's lesson. Next lesson we're going to be looking at the electromagnetic spectrum. We're going to be looking at as many of the aspects of the electromagnetic spectrum as we can, just because obviously the point visual light is a very small part of that. But as I said, that will be our next lesson. My name's Ian McDowell, I'm a student at Brighton University. Thank you.